Hello. Shall we get started? Good afternoon, ladies and gentlemen. My name is Moritz Lenz, and I'm a physician both by education and profession. So today I'm going to talk to you about something which I actually understand, which is not programming but physics. I will use programming, however, and we'll use some physics models that I've written. So this is what I'm going to present. And first I'll start with physical modeling. What is a model? What do we use it for? Is it this one? Is it that one? I'll show you an example of a simple model. I will do a very short recap of mathematics, what is derivative, and then model as an object in free fall, and then going to put up a spring again, and then I'm going to talk about resonance. So, we physicists try to understand the world somehow, but it's actually far too complicated to just look at it and understand what's going on. So we just pick some essentials, some essential properties that we look at one point. For example, the motion of an object instead of its color. So this is what we call a model, and so it's basically just a very broad simplification of the real world to some very few variables. So, for example, we have here an image. You can see the spring at a swing, and a woman on that swing, and in the background some trees and so on. But when I want to describe the motion of the swing, I'm not interested in that. I'm interested in there's a mass somehow here, or maybe two masses if I want to have some kind of rotational movement, and I'm interested in angle bond, and I'm interested in the gravity force, and I'm interested in the velocity of that object. So that's what my model will take into account to try to do something about it. So it will be gravity, inertia, motion, and connection to angle point, and maybe later such things as air drag also. And it will suddenly neglect other things, like actually far more than I listed here. It will neglect colors, exact shapes of the objects. It will neglect their size even. It will neglect friction, for a start at least, and about hundreds of other things that you can think of, like the trees in the background. So, when you do such a simplification, we have to ask, don't we miss something essential? Because if we don't know yet how this thing works, that could very well happen. So, the question is, the model is a good model, can only be answered in context, and that context is the question you ask the model. So we can ask, how fast is that object moving, or what's the period of that woman swinging on that swing, or does the distance to the angle point influence the frequency? And sometimes the accuracy of the answer might be important. Like if you ask what is the velocity in meters per second, but sometimes it's not very important. Like we just want to understand some basic concepts, like does the gravity force influence the period, and then finally we need some input data to run our model. So for example, we would certainly need the gravity force, the value of the gravity force for that model, and if we have no way of obtaining that data, then our model is useless because we can't do anything with it. And often we also want models to be extensible, because like software, we want to be able to add air drag, for example, if we consider that important, and we basically don't want to write a whole new model for that. So here's an example model I want to discuss. We have here an object starting at near the top of the leaning tower, and we just let it fall, and we want to see for example, how long does it take to drop this object to the ground? And we certainly will need the gravity first, and we'll neglect everything else for now. So this is how my solution to that looks in physics. And I use this module called Left Model, which I've written, and I instantiated what we call mu, and I declared some derivatives, which I'll declare later on in more detail, and I also have some auxiliary variables, and I also have initial values. So I say we start at a height of 50 meters, and we have no velocity to begin with, and then I say which variables am I interested in the end, and then I do this weird called integrate, and the time axis starts at 0 and goes to 4 seconds. I have no clue why I took that value, which is it. And I also have some additional things like minimal resolution, which we can add for now. And then I render the result as a scalar vector graphic, and then title and refining. So this is what the result of the model looks. On the right hand side, you can see the time axis, and to the top, there's the height, axis with the blue curve. The blue curve is the height in meters, and the yellow curve, which is actually not a curve, but a straight line, is the velocity in meters. And you can see that since our coordinate system points upwards, the value of the velocity is negative, which means that it falls down. And you can also see that in the beginning it's at 50 meters, and then it comes down in a parabola shape, and it hits the ground after about 3.2 seconds. But in our model, it doesn't hit the ground because we didn't model the ground. It just falls through. Like imagine there's an infinite deep hole in there, and it just falls there. And for example, if we want to know if our object is destroyed while it hits the ground, then we should take that into account. But if we just want to know what time it takes, it's perfectly fine to omit the ground from the model. So I promised to talk about the derivatives in more detail. So what we do here is I declare that the velocity is the time derivative of height, and the acceleration is the derivative of the thing called velocity. And if you don't know or remember what a derivative is, it's basically just the slope of the curve in any point. So if I want to know the derivative of this curve here, somewhere here, I draw a triangle with axis parallel to the axis of my coordinate systems, and then I can see where it intersects the curve, and I have height, which is negative, and width, and the slope is just the height over the width, and to get an accurate result, we just have to choose a very small triangle. And that's what we call the derivative. And it might be useful to you, if you want to write such models yourself, to know what kind of derivatives there are. And for example, in mechanics, we have velocity is derivative of position. So the velocity describes how position changes over time. And by the same terms, we can say that the angular velocity describes how an angle evolves over time. The acceleration describes how the velocity evolves over time. Power is the derivative of energy, force of momentum, which, if you remember, is mass times velocity. And there are also other fields where we deal with derivatives. For example, in electronics, the electric current is the time derivative of electric charge. And if you take the difference of birth rate and mortality rate, you end up with the derivative of the population. And profits or losses are the derivative of funds available when it comes to a company. have to know the value that's being derived from, but only the value of the derivative. But we have to provide an initial value for the quantity that's being derived from. And if anybody is more inclined with math, what I write down is a set of ordinary differential equations with which math model integrates for you with any adaptive step size from the Cotta integration. But if you didn't understand that, you can just as well forget it again. So the rest of the model I mostly explained. What I didn't explain here is the variables. I've put here that the value of acceleration is just the same value as the gravity, and the gravity has the value of minus 9.81 meters per square second. These initial values are around set. I think I've covered the rest already. So, since this is a programming conference, I feel I have to tell you a bit about programming. This page has a colon here after the dollar, which makes it a name parameter to the block system. You can see here. Let's take gravity instead. It is enclosed to the block, so this is the name parameter to the block. And what math model does, it is introspects the blocks and parses, gets a list of parameters, and then it uses topological sort to calculate the dependencies among these variables, and then it finds the execution order among them for each integration step, and then it uses this roller coaster method which I've mentioned, which is not important. So let's extend the model a bit. Here I've added a spring which is anchored to the top of the tower, and if we let our objects fall down, it will at some point experience a force going upward. And yes, let's see how we can model that. So I've just added here more terms to the value of the acceleration, which is the acceleration of the spring, and also a dimension term. There's also a curly brace at the end, but it somehow can come off. So I should also mention that I've changed the coordinate system, and the top of the tower is now at 0. So in order to get a force upward, we have to take minus something proportional to the height, so that the spring force is proportional to its length. And I've also added some damping, which is usually proportional to the velocity. I've just chosen some arbitrary value which produces pretty pictures in the end. So this is how the height looks like as a function of time. And you can see that it's, as promised, we start at 0 and it goes down, and sometimes the spring goes up again, and it oscillates, and due to the damping, the height of the oscillation reduces because of the amplitude which reduces. And you can also see that it has a frequency which is intrinsic to the system, by which I mean that it's the